In this video, we're going to deploy a complete distributed tracing stack with Tempo, Alloy, and Grafana using Kubernetes. We're going to explore the entire setup and analyze traces flowing through a multi-service application. We're going to use the traces to identify performance bottlenecks using Grafana's Trace Explorer. We're going to learn how to visualize service dependencies and get an overall understanding of performance issues with the service graph. And we're going to explore advanced visualizations with the Traces Drilldown plugin. I'm going to provide all of the project files you need to follow along step by step. So let's just go into it. All right, we interrupt this broadcast with a very important message. If you haven't subscribed already, come on, hit that subscribe button. You'd be doing me a favor. All right, see you in the lesson. All right, inside of your video description, I left you a link to the following GitHub repository. Make sure that you go to it because this repo contains all of the code needed to follow along with this YouTube tutorial. And after you're done watching this video, if you want a summary of everything we talked about, there's a written article that does exactly that. But definitely recommend watching the video first because I go into a lot more detail. Now, there's one more thing I want to mention. I recently released a platform under my own domain, ryanslim.com, where I intend on releasing a lot of cloud and DevOps courses. The reason these courses will be different than the stuff I release on YouTube is that they're going to have a lot more structure and be a lot more comprehensive. Okay, so if that's something that you're interested in, make sure that you join the waitlist. So far, I've only got 5 people who signed up, which is not enough to encourage me to start making these courses. But if I can get enough interest from you guys, then that's something that I'm willing to kickstart. All right. Anyways, do make sure to sign up. Let's get back to the lesson. We're going to clone this repo inside whatever directory you want. Doesn't really matter. I'll clone it in a directory called YouTube tutorial. Once it clones, go ahead and launch it inside of a text editor. I'm going to be using VS Code, and let's get this party started. So these project files contain everything that we need to set up our distributed tracing stack. But before we do, I want to first make sure that we actually understand why we're doing what it is that we're doing. So distributed tracing is important because imagine a scenario where you have a user sending over a request to our application that's composed of many microservices. Let's assume the request ends up taking 5 seconds, a very, very long time. But because the request went through many microservices, we don't actually know what the bottleneck is, where the request stalled the longest. And that's why distributed tracing is important, because it allows us to trace the life cycle of the request as it hops from one microservice operation to another. And so if we can actually measure and get a granular look at how long each operation took, each span took, we can determine what the slowest span was, what the slowest microservice operation was, fix it in order to ensure that future requests don't experience the same downtime. They can actually be processed a lot quicker. So that's why distributed tracing is important. We're going to deploy the entire distributed tracing stack right now, but before we do so, we need to simulate some traces. Now, don't worry, we're not going to deploy a multi-service application. For the purposes of this video, what we want to do is mainly focus on the distributed tracing stack, and in order to generate some traffic, generate some data, we're going to use the K6 trace generator. And ultimately what this does is it spins up a container, spins up an application that generates traces which simulate requests going through many microservices. And all of the traces that get generated, we're going to send them over to Alloy on its port 4317. So Alloy is an agent for collecting telemetry data. That's pretty much it. It's the agent that's going to be collecting all of the traces that get generated and eventually send it over to Tempo, the back end that stores all of the traces. So by passing in this environment variable, the K6 trace generator is going to know to send the traces to Alloy on its port 4317. Remember, 4317 is the standard port for the transmission of telemetry data. And then remember, Alloy is the agent that essentially just collects telemetry data and forwards them to the appropriate backend. In this case, it's going to send over all the telemetry data to Tempo, which is configured using this tempo values.yaml file. We'll get into the Helm installation in just a second. And this part is really cool because Tempo, not only does it store all of our traces, but using the traces, it's also going to generate a lot of Prometheus metrics, which we're then going to write into our Prometheus database. And so two types of metrics will be generated: service graphs and span metrics. Service graphs metrics will allow us to construct a graph that links all of the microservices and allow us to explore the interdependencies between them and isolate which microservices are experiencing the most failures, which ones are the actual bottlenecks, which ones have spans with the slowest processing times. And span metrics, you'll recall I defined a span as a unit of work within a microservice, a single operation. And so what a metric is in this case is it will aggregate all of that span data into measurements that allow us to extract very meaningful insights, like what the average span processing time is across all microservices, okay, what the slowest span processing times are. And so all of these metrics that get generated, they're going to be written to Prometheus, into the Prometheus database, and Prometheus is going to enable the feature exemplar storage, which will essentially allow us to bridge all of the Prometheus metrics to all of the traces. And essentially, this is going to create a very beautiful workflow where we can use the Prometheus metrics in order to sound the alarm bells when we see, very high processing times across many spans, and then bridge those metrics to the traces that caused them, and then look at the corresponding traces and spans to actually pinpoint what it is that's actually causing the problem. Okay, so we're going to use this Helm values.yaml file to install Prometheus as well as Grafana that's going to visualize all of the trace data inside of Tempo, as well as all of the metric data inside of Prometheus. Now, by default, it's already connected to the Prometheus data source, but we're also going to connect Grafana to Tempo. Okay, so these are the values file that are going to steer the deployment of our Helm charts. And now we're actually going to use Helm to install all of our stuff. Okay, so I spoke a lot, but let me go back to my GitHub repo. So one thing I failed to mention is there are prerequisites for this tutorial. You need to have access to a Kubernetes cluster, whether that's local or on the cloud, doesn't really matter, and Helm installed. If you don't check out these tutorials, then go to setup. We're going to view the markdown file from GitHub because it has a nicer UI. Okay, let me just put these side by side. First thing we'll do is create a new namespace, monitoring, where everything is going to be deployed. Then we're going to add the Helm repositories that contain all the necessary Helm charts we're going to leverage. So the Grafana Helm repo is going to contain the Helm chart for Tempo and Alloy. This is going to contain the Helm chart for the Prometheus stack, which we're going to use to set up Prometheus and Grafana. So go ahead and just copy this command over. Just the way it is. Windows users, please use git bash if you want this format to work for you. I put a -- wait to wait until everything is fully set up before it outputs anything. So everything is working. Now we'll go ahead and deploy Tempo. That's going to take some time as well. I'll be back in a sec. That should take a minute or two. Okay, beautiful. Now we'll deploy the agent Alloy. Okay, so remember Alloy is going to be sending everything over to Tempo. That's going to be storing all the traces, generating metrics, which will be stored in Prometheus. Grafana is going to visualize all the metrics and traces. We're going to have lots of fun, but we can't get anything started until we deploy the trace generator. Okay, So that's been generated. Okay. Let's just make sure everything is good before we proceed. kubectl get pods -n monitoring. All is well. Let's make sure K6 trace generator is actually generating traces. Beautiful. So it's generating a lot of traces. They're all being saved to tempo. We can visualize all of that in Grafana. We'll need to do a little port forward in order to actually access it from our host machine port. So let's get all the services. kubectl get service -n monitoring. Okay, which one is the one that we're actually interested in? Monitoring Grafana. So we'll say kubectl port forward service /monitoring Grafana. Didn't even write the whole thing. The cluster IP port 80 will map it to port 3000. All right, so make sure you do that on a separate terminal because you don't want it to close, or you could run it in the background, doesn't really matter. Services monitoring Grafana not found because I should specify the namespace that it's actually in. All right. Let's make this a little bigger. Localhost 3000. You shouldn't really need to log in. Explore. Press search, and let's get started. So you may notice my appearance change because I did film the rest of the video last week. So anyway, everything should still be consistent. See you in there. Click on search, and here you should see a lot of trace data. If you don't, just run the query in order to refresh, and there you go. I'll go over what all of these options are in just a second, but let me just start by highlighting all of these traces. Each trace represents the complete journey of a request as it starts from the initiating service and propagates through our distributed system of microservices until a final response is sent back. So here we see that the initiating service for every single request that was made is always the shop backend. So we've got all of these services that are running, ready to process our request, and the front door to all of these services appears to be the shop backend. So that's info that we get from our traces right away. Beside the initiating service, we see the initiating span, the root span. Remember that a single trace means one request, and in that request there are many spans, many operations can be invoked. The initiating operation is the root span. So we can see that for every operation that was initiated per trace, most of them don't really take that long, between 500 to 600 milliseconds, some 700 back to 500, but here we see that this operation that was initiated took 1 second. So why did this request take so much longer than the others? We can drill into the trace to find out and identify any potential performance bottlenecks. Let me just zoom out a little bit. Okay, I'm going to start by just looking at the root span. So when the request is first made, it reaches the shop backend microservice, which invokes the operation article to cart. And this operation overall took 1 second, one whole second to process, 1.05. Aside from the fact that this operation was slow, we don't really get that much more information. So we need to drill into the trace in order to really identify the bottleneck and look at what's going on. So this operation invokes 3 other operations that get executed in parallel. We can identify the names of these operations as get article, place articles, and authenticate. Beside each operation, each child span, we can see the microservice where it's being executed. So if we drill into this child span, so here we're still in the shop backend microservice. Notice the color hasn't changed, but then the request gets transmitted to the article service microservice. And the get article operation in this service overall takes 450 milliseconds to process. It invokes an operation called select articles, part of that operation being a Postgres query, which took 200 milliseconds overall to process. So this child span took 600 milliseconds, not bad. But then you've got this child span, which took approximately 800 milliseconds. So eventually the request from shop backend is transmitted to the cart service microservice, which invokes an operation called place articles. This span takes a very long time because if we look at what it does, it tries to perform another operation called persist cart, which took 470 milliseconds to process. So this tells me the persist cart operation inside of the cart service is really, really slow. And there's something I need to do in order to optimize this function in order for it to run faster. And so I can look at the authenticate span and conclude that that one wasn't problematic at all because it invokes another operation, again called authenticate, inside of the auth service microservice. That one only took 70 milliseconds, which tells me that the root of my problem isn't authentication, isn't retrieving an article, but actually placing an article and persisting the cart. This is the function that I need to optimize, okay? And all of these operations are happening in parallel. We can tell that because, as you can see, the operations, they're not being processed one after the other. The bars are all being processed concurrently, simultaneously. It just so happens that this operation just takes a much longer time to finish, essentially stalling the entire request as a whole. So we've essentially just analyzed a complete trace. Simple as that. Just look at which traces take the longest and try to see what's going on with them. Okay? And what you can do in order to assist your analysis is filter based on duration, let's say. So you could say only include requests that took longer than 1,000 milliseconds. So 1 second. Run the query. Oh, I forgot to add milliseconds. Run the query. And here we see the article to cart operation from before show up first. So very, very useful to be able to filter by duration. You can also filter by span name. The only span that shows up is article to cart, which is a big indicator to me that only the article to cart operation is what's experiencing the biggest bottleneck. Again, then you would go into the trace and identify what specific function within this initiating span is actually the one that's causing us a lot of trouble. All right, so removing this 1,000 milliseconds filter, we can see many, many more spans to filter by. And what this essentially does is it only includes traces that have this child span somewhere within the request lifecycle, okay? And then it seems like only services that include the Postgres database can be selected for this particular span. And no matter what, the shop backend service is always going to show up as the name because it is the initiating service where everything is happening. So if we look at this trace, we can confirm that the query article span is an operation that is exclusive to Postgres. That's why the filter limited us to just filtering by the service name Postgres. But if we close this, remove the span name, we can filter by many services, card service, billing service, whatever. If I put billing service, the service name that shows up is always the initiating service that receives the request and propagates it to all of the relevant microservices. So that's that for filtering. Now the next thing I want to do is go to the service graph. And here we've got the very valuable service graph, okay? Now you'll remember that Tempo was configured to generate Prometheus metrics based on all of the trace data. And it's these Prometheus metrics that allow us to construct this very beautiful service graph, this very valuable service graph. It's not just easy on the eyes, it also helps us analyze performance issues as a whole and give us an overall understanding of what the bottlenecks are within our distributed system and tells us where to start looking. Okay, so while this gives us an overall understanding of the performance issues, we can then drill into specific traces in order to investigate specific performance bottlenecks. Okay, so usually the first step before drilling into particular traces is to look at your service graph, okay? Starting from when the user initiates the requests. We can see that our users, or in this case, the user, is making 0.33 requests per second. It follows that the shop backend microservice, which is the entry point into our distributed system, is going to have the same rate, all right? And we can see that requests in the shop backend take 655 milliseconds on average to be processed, okay? Now, what's beautiful about the service graph is it tells us the interdependencies between different microservices, and because the auth service has the same request rate as the shop backend, this tells us that every single request that goes through our entry point needs to be authenticated. But it seems like 20% or so of our requests don't actually get authenticated properly, because the green is actually a health indicator telling you whether or not your application is healthy. But because this has a lot of red, that means most of the authentication requests are actually failing and sending back errors. Okay, so something is clearly wrong with our auth service. And if we scroll up, we see the authenticate span, the authenticate operation, which likely belongs to the auth service, that has a request rate of 0.33. We just talked about that, but an error rate of 0.08 errors per second. So as we just said, almost 20% of the requests that this microservice is getting, almost 20% of them are actually failing, 0.08 errors per second out of the 0.33. And here we see another valuable Prometheus metric, the 90th percentile for the duration, here telling us that 10% of all of these authenticate operations actually take 490 milliseconds to process. So if we consider that the overall duration of requests going to auth service is 186 milliseconds, then we can tell that the successful requests are actually bringing our average way down, and these unsuccessful operations, if we fix them, it should further optimize our average request duration. Okay, so that already gives us a starting point as to what it is that we need to fix. Okay, and here we see other spans based on descending order of the rate. All of them get processed successfully. None of them show any errors, but you can see the list articles, place articles, the one that we talked about before, and get article, all of them take 800 or so milliseconds. So it makes you wonder, why are these taking so long? Well, you remember that Prometheus was deployed with exemplar support such that we can bridge the Prometheus metrics with specific trace data to go from analyzing performance issues as a whole to drilling into the traces that are actually causing these issues. So remember, we talked about that top 10% of requests having this duration, and we're seeing that 10% over here that are bringing our average way up. Okay? So pretty cool how we can bridge metrics and trace data. This helps engineers extract very valuable insights and identify performance issues right away, because this tells you where to look and this tells you exactly what the issue is. And anyways, we see that because most requests don't get authenticated properly, I'm assuming the way this distributed system was programmed was to just not propagate that request, which is why we see much lower request rates for the article service, because I'm guessing it just abandons it and sends it back like a 403 error or something. Anyways, so that's it for the service graph. The next thing I want to point you to is go to localhost 3000 /a/Grafana Explorer Traces app. Okay, so this is just a Grafana plugin that provides an opinionated way of looking through your span data. It's not necessarily more or less valuable than the other methods we looked at before with your service graph and your traces drill down view, but it's something worth knowing anyways. So it starts by filtering and focusing on the root spans, so your initiating spans inside of your shop backend. And it starts off with a graph that shows you how many times the initiating spans were executed per second. So 0.286 spans executed per second, 0.357. It follows that these graphs are going to be identical because the initiating spans are inside of the shop backend service. So whenever each initiating span is executed, basically a request was made to the shop backend microservice. All right, 0.214, 0.214. Anyways, root spans doesn't really give us much to go with. It gives us an overall view of what's happening. But if we look at all spans, obviously this value multiplies, because when one root span is executed, many child spans are executed as a result. Okay, so let me go ahead and look at another graph, something more interesting. Actually, before I do, here you can see all the requests being made to different microservices. Obviously, the shop backend microservice and the auth backend microservice are going to have the same values, because every request that goes to shop backend, as we concluded earlier from the service graph, needs to be authenticated first, and not necessarily all requests are going to be authenticated properly, which is why we end up seeing much lower values for the subsequent microservices that don't end up receiving all of the requests. Okay? So a more interesting graph is this one. So click on it, the histogram by duration. This heat map is really powerful because it allows us to visualize how our spans are performing as a whole. So the lighter the color, the higher the frequency, the lower the color, the lower the frequency. So here we have the highest frequency at 1308. It seems where 33 spans belong to the bucket 268 milliseconds. 31 spans belong to the bucket 537 milliseconds. 28 spans belong to the bucket 1.07 seconds. So gives us a general understanding of how our operations are performing as a whole. We've got some pretty fast spans and we've got some pretty slow ones. Let's go over to the slow traces tab. And what this does is it puts the slowest traces on top and ranks them in descending order. And we can click on the trace name for more detail in order to really understand what it is that's going on. I'm not going to go through this process again, but we can clearly see what the performance bottlenecks are. We got the child span here that takes 1.02 seconds. We've got get article that takes 982 milliseconds. They both happen in parallel, but ultimately we end up with an overall article to cart route span that takes 1.19 seconds. All right. And here we have the root cause latency, which again shows you all the slow spans, but allows you to analyze their structure, very similar to how we did it before. So you're welcome to use the plugin. You're welcome to use the service graph as well as the trace drill down feature, which is honestly what I use. Hope you enjoyed this video. If you did, make sure to hit that subscribe button. Do check out my website, rayanslim.com. Join the waitlist so that I may be encouraged to make courses. And yeah, see you in the next one.